We are going to go into the details of the oxygen dissociation curve of hemoglobin. When hemoglobin is about to bind to the first oxygen molecule, it has a shape whereby this binding to the oxygen molecule is difficult. It has a more closed structure. So at low oxygen concentrations, this will not work most of the time. Not a lot of oxygen will bind. And this is why the curve is usually low initially. But once this oxygen binds, this first oxygen binds, the shape of the hemoglobin molecule, the quaternary structure, is going to change and take on a more open shape. This is going to make it easier for the remaining three subunits to bind an oxygen molecule each. So the first binding is difficult, but the ones that come after that are easier. So in order to accelerate this binding, the binding of the first oxygen molecule, you have to really increase the partial pressure of oxygen. You have to increase the amount of oxygen present so that this first binding becomes faster. However, if you want to accelerate the second, third, and fourth bindings, you don't need to increase the partial pressure of oxygen that much, since it is already easier for them to bind than the first oxygen molecule. This property is called positive cooperativity, which means the binding of the first molecule makes the second binding easier, and so on. And this is why in the curve of oxygen association and dissociation, we have the gradient steepening. However, when the third oxygen molecule binds, we expect the fourth one to have an easier binding. However, in reality, the binding of the fourth oxygen molecule is harder. And this is just due to probability, because now we have 3 out of 4 sites that are occupied on the hemoglobin molecule, so it's less likely that this molecule of oxygen will find an empty site for it to bind on. So the second oxygen molecule had 3 spaces to occupy, so there's a lot of probability for it. Probability is on the side of this molecule. And the same happens for the third. However, the fourth oxygen molecule has to actually look for the empty site, the single empty site on the entire protein, to sit on it. And so this is why, at the end, the gradient of the curve will reduce and the curve flattens.